Okay, here we go. So, first class, we touched ground. Was it too much? Was it good enough? A bit challenging, I imagine? A bit challenging, yeah? So, I mean, do you love SuperCollider?
No.
No. Anyone? No one?
No, love and
Okay.
hate.
It's kind of okay? Not really?
Love and hate.
Love and hate? Only hate? Or love and hate?
Mostly hate.
Mostly hate, and you?
Only hate.
Only hate. Well, sounds like I have a challenge. I mean, we can always talk to Balázs and ask if he agrees we do this in Max MSP. Everyone loves Max MSP? Not even. In that case, it's not an issue then. But I will have to check because this is the practical side. Did you bring laptops?
I can't bring my laptop, unfortunately.
Okay. Well, in that case, after the break, or maybe now already, you can bring in one of the computers outside.
But I have my iPad with
Can you code SuperCollider on this?
no support.
So we need you to get a computer going. Okay. So I mean, my idea was to actually start with this already and just see how you can do some basic code, if you can do some basic code on your own. I have been fortunate or unfortunate to see how audio programming becomes copy and paste of the code and students get marks without being able to code at all. Unfortunately, this seems to be the situation because there is a pressure, okay, you should study programming, but if you don't have some background or some motivation or some talent for this, it can actually break down very quickly. So I'm very reluctant to go with anything before I'm sure that you can, just code the basic sine oscillator or some oscillator with a filter or something like this. Okay? So we'll do this. I'll do a bit of theory then and a bit of showing you stuff, and then probably take. Maybe we have a long session today, so maybe 2 short breaks will suit. But you guys are always welcome to let me know how you feel and if you need a break, anything like that. Okay, S-boot, you guys know this one. Do you guys know how to get help files working and all the rest of that?
Actually, I have a question.
Yes.
I have a problem.
Mm-hmm.
I don't know for how long.
Mm-hmm.
So I try to boot my server, and there's in the console it says like it exited.
We can have a look at it later. I cannot know it from heart. When they start to find their computers, you have a PC?
Laptop here.
PC or Mac?
Windows. Yeah.
Windows. I'm afraid I have no clue about Windows. I can check it, but did you try ChatGPT and generic?
I asked. We tried to figure out this with Balázs this morning because the thing is, it doesn't even show what kind of issue is it. It's just running the server.
Did you try to install a different version of SuperCollider?
Oh, and it worked last year.
Try a different version of SuperCollider, check online, ask the questions. We can also try, I mean, I didn't use Windows for probably 20 years now, and I have no clue. Cool. So, what we've done in the first class, you guys tell me, who remembers? What have we done a week ago?
We talked about the ranges.
Ranges, very good. And we did some range conversion, and the other thing? Curvatures.
Yeah.
Curvatures. We talked a bit about exponential scaling, a bit about curvatures. We did a bit of crossover network design in the end, right? So we just figured out what is the spacing, what is the equal spacing on frequency axis. Okay, now last year we've done, spring I guess, we've done stuff with multiplication and addition, and now we've looked at the exponents. So what can you tell me? I'm curious how much you might remember. What happens if I square a sine wave? I multiply a sine wave with a sine wave of the exact same frequency. What happens?
Square wave?
Nope.
Or just the amplitude is
Nope.
Modulation.
So the term we used, huh? Huh?
Depends on the frequency.
I've said the exact same frequency. So 100 hertz sine wave, I multiply with a 100 hertz sine wave. What happens? So the key term to remember is sidebands.
yeah.
Can you now recall what does it mean that we are going to get some sidebands? What are the sidebands? Well, it's gonna be tough to get far if you neglect the basics. So obviously I'm here to match the level and try to get you guys up to speed. So what happens when you multiply two sine waves, you get sidebands, which will be the sum frequency and the difference frequency of the two original sine waves. Okay, so if I multiply 150 hertz sine wave with a 200 hertz sine wave, which frequencies will I get?
Some 300.
Sum is how much?
You said 100 and 200?
Let's say, I said 150, but never mind.
Oh, sorry.
No, it's okay, it's okay. It's easier, because then this difference won't confuse you, okay? So it's 350 and? Difference between 150 and 20?
150 and 20.
Yes, what is the difference between 150 and 200, sorry?
250.
50, yeah, exactly. So you see, you can kind of visually appreciate why we call them sidebands, because they come to the side of the original frequencies. Okay? What happens to the original two frequencies? They disappear. They're gone altogether. Is there a way to preserve the original frequency?
Reverse phase.
No. But good thinking, yeah, there is a way. We've studied this. So what happens if you multiply bipolar sine waves? Which bipolar, you know, guys, what means? Can you tell me what is bipolar?
Multiple.
No. Bipolar signal, what does it mean? Hello.
Hello. It has ground.
Uh-huh.
Ground and
No, we're not in the electronics class. We don't have grounds.
The opposite phase.
No opposite phase. It has to do with the range of the signal. A bipolar signal has a range, minimum in the negative and the range maximum in the positive. It's bipolar. It has both polarities. Plus and minus are the two polarities. Okay, so it's bipolar. And we have unipolar signals, which have a single polarity, typically positive. Okay? So there's the key. Anyone remember now? So if I multiply bipolar sine waves, I get sidebands only. If I multiply unipolar sine wave with a bipolar sine wave, then the original frequencies are still there. Okay? What are the names that we use for this? Bipolar multiplication is called ring modulation. Yeah. And if I multiply with the unipolar sine wave, it is called amplitude modulation. Okay. So, I mean, I'm doing this obviously for the goodwill. It's not about, oh, you naughty, stupid students. It's about, okay, let's repeat it until it sticks, but it actually has to, the way this will stick is if you explore it yourself. Okay, who can tell me what is aliasing? We've done this last year as well. So aliasing is a spectral phenomenon. What is spectrum? Can anyone define spectrum? What does it mean, the word spectrum?
Frequency.
Yeah. So typically in this context, the range of audible frequencies is what we refer to as spectrum. But in a different context, it could mean different frequency ranges. Hello. Pass. Okay, so aliasing is a spectral phenomenon whereby frequencies which go beyond the Nyquist frequency. Can anyone tell me what is Nyquist frequency?
Inaudible?
No. I mean, it could be, but it doesn't depend on audibility. Nyquist frequency is the half of the sampling rate. Yeah? So, what is a sampling rate? Can anyone define sampling rate? Mm-hmm.
The rate of which computer calculates?
No. It's not the rate of the computer, it's the rate of the sound card. Okay? So what is the typical sampling rate of a CD quality audio? 44.1 kilohertz, yeah, okay. So that is essentially horizontal resolution. So if I have a higher sample rate, it means I have more points in time. So I increase the time resolution of the signal with higher sampling rate. What is the vertical resolution of digital signals? No. Decibel is actually a unitless measure. We do use it a lot in acoustics to talk about amplitude, but it is not the vertical resolution of a digital signal. Instead, bit depth. Very good. So what is the typical bit depth of audio quality digital signals? I mean CD quality? 16. 16 is the CD, and then obviously we can go higher. Okay, so we have these resolutions in time and in amplitude, horizontally and vertically. Cool? Now, what is aliasing? Aliasing is a hugely important chapter. It actually, to put it simply, describes a mirror type phenomenon, which is at the Nyquist frequency, which is at half the sampling rate. So if I have my audio running at 44 kilohertz, half that 44 is 22, and I actually have a mirror at 22 kilohertz. And what it actually does is everything that potentiates to be of a higher frequency will never be of a higher frequency, but it will be mirrored back. So this means if I try to synthesize a 30 kilohertz signal at a 44 kilohertz sampling rate, I will actually get 14 kilohertz signal. So you can do this with addition subtraction. So 30 minus 22 is 8, and it's mirrored back, so I need 22 minus 8, it's 14. Yeah? So that's aliasing. So why was this important? Well, the first entry into this concept comes typically from study of digitization of a signal. If you have an A to D converter, what does that stand for, A to D? Analog to digital. So if you want to digitize a signal, then you have this issue that if there is any signals too high in frequency, they will actually create problems, audible problems. So I can actually digitize an inaudible signal and get an audible one. because of this mirroring effect. Any clue, how do we mitigate this problem?
Limit the sample rate.
Actually, regardless of the sample rate, you have to do one thing to exclude the potentially problematic frequencies. Filter. Okay, so typically you have a digitization filter somewhere in the line. Okay, now in terms of synthesis, aliasing is also hugely important, because if I synthesize a square wave by switching between +1 and -1, it will be aliased square wave. So it won't be clean. Okay, so I'll try to demonstrate that. Now, let me just make sure I get the audio here. I probably need to, again, server kill all. Okay, and now headphones, great. Speaker seem on, let's see. So let's get a test signal first, sine oscillator, favorite frequency, dot play. Okay, here we go. Okay, so let's check out a square wave. And what you, I hope, will remember to use in terms of the terminology here is aliased oscillator or a geometric waveform. Okay, so square wave, triangle, sawtooth, these are geometric waveforms. So LF pulse is, you see it says non-band limited. Okay, so this is the other term, which means that it's aliasing. So band limited means that it's made such that it fits into the valid usable range. If it's non-band limited, it doesn't. Typically, it is much more efficient, much more quick to create a geometric waveform than to create a proper band limited square wave, which I will talk about in a second. So let's check out a square wave like this. So we have a frequency, let's say 500. We have a phase, not worried about that. And we have the width. Any idea what is this? What is the width parameter? What does it signify? It's also called pulse width. And it's also called, in a slightly different context, let me see if I remember. Well, yeah, pulse width, pulse width. You have pulse width modulation, you might have met this one, PWM. So what is pulse width for a square wave?
It limits so the square wave doesn't sound as harsh.
It's a geometrical parameter. So the pulse width does have an audible impact, but it's not the audible impact that defines it. What defines it is the geometrical property, namely, any ideas? It kind of tells you already, pulse width. So from an actual square wave, which is symmetrical in the middle, that would be pulse width 0.5 or 50% pulse width. And then you actually move the middle line, so to speak. So the period of the square wave stays the same, and the period defines the frequency. But the middle line, so the ratio between +1 and -1 parts, is changing. It's moving. That's your pulse width. Okay? So for now, I'm not interested in the pulse width. So I just want a 500 hertz square wave, which is non-band limited. And actually from this, you probably already hear that there is something fishy. It doesn't sound like a clean square wave. In turn, a clean square wave will be, if I remember right, pulse. So you see the difference? So we can observe this difference in spectrum. And actually what you see there is in comparison to this one, the clean one, you see technically the square wave should have what type of harmonics?
Even.
No?
Oh.
Odd harmonics only. Okay, so this is my fundamental. Well, it's supposed to be 500. I don't know who you should kill for this one. It's below 481. Sorry. But you can probably see that if I assume this is 500, this is actually much more than 1000, closer to 1.75. This is 3 times that frequency. This is 1.5K. And then this is 5 times the frequency and so on. So only odd integer multiples. And there is an equation, which I won't bother you with much, that would specify what is the amplitude of each harmonic. And it should be a monotonously decreasing series of harmonics. And there is something worrisome happening there, I must say. But let's see this one. This one should be even more worrisome. Oh, that was the one. Huh? This one and then this one. Yeah, well, this one is more worrisome. So what you actually get, you see all this energy, it's just all further up. It's because everything that wanted to, so to speak, reach beyond the Nyquist frequency was mirrored back into the spectrum, and typically you kind of see this backward dropping thing happening. Okay? Cool. So this is the case with all the geometric waveforms except sine wave, because it doesn't have harmonics. Does anyone remember what is the only way to synthesize a band-limited geometrical waveform? You actually have to add up all the sine waves that you know constitute this signal. You cannot create a square wave geometrically and get rid of aliasing. Because if you start filtering in the high frequencies, then what will happen is you will also filter out the harmonics that are a genuine necessary part of the square wave. So as soon as you create it geometrically, you're dead. There is aliasing. You cannot cure it afterwards. So because we know the equations in terms of the constituents of the square wave in terms of sine waves, we actually add up all the sine waves. And this means that depending on the frequency, you will need more or less oscillators to produce a band-limited square wave. Okay? Cool. Now, envelopes. What is the simplest envelope? You guys know the term?
Radius.
No, that's a very complex one. The simplest one is a ramp. Okay, so a ramp is a signal that goes between two values linearly. That's a linear ramp. You can have different curvatures as well. Okay, so what I would like to show you then is what happens if I, instead of keeping this frequency fixed, I actually run it from 500 to 5000 in 5 seconds. So what you've seen there is how the harmonics disappear, right? And you see that actually at 5000 hertz, I only have a single harmonic left. Okay? So this signal, if you check it out with the actual scope, doesn't look anything like square wave. Okay? At this stage, it starts to look like a sine wave, pretty much. Let's see. This is how it looks like. Right? So it doesn't look like square wave at all. And if I take the actual geometric square wave, well, that's quite solid square. So you get it, right? If you have a geometrically perfect waveform of this sort, it will be aliasing. It looks good, it sounds bad. If you have an audibly perfect geometrical waveform of this type, then it looks bad, but it sounds good. Okay? Curious, isn't it? Okay, so did anyone notice what's weird here? Is this a unipolar or a bipolar signal? Huh? Unipolar, indeed. So that's one issue as well. How can I make it bipolar? Well, I can convert the range. -1 to +1. Now it's bipolar. Cool? Cool. Now, this was the sweep. Let me just show you. I hope it's gonna work out. I want to show you approximately what a fixed frequency band limited square wave looks like. Let's take 100 Hertz. And I think I can. What was the trick? I think there was this trick to stop it. If I. Not really, huh? In any case, you kind of see it. I can try to make it in sync. Essentially, what you get is that here at the corners, you don't have a sharp corner, but you have a kind of a tiny little oscillation instead. This is what a perfect digital square wave looks like. Mind you, in the analog domain, this does not hold. In the analog domain, you can use a switch between two levels as rapidly as you want, you will not get aliasing. Just does not happen. Okay, so this is a phenomenon that holds for digital signals. Okay, now if I take a ramp between 500 and 5000 and use it on a non-band limited square wave, what do you expect to hear? Can you envisage this? So you saw me doing this for a band limited square wave, and what happened is that the harmonic suddenly disappeared. The actual oscillator internally was switching off oscillators as I increased the frequency because it just didn't need that many sine waves. For a 5 kilohertz square wave, I only need 2 sine waves at this sampling frequency. Okay, so can you predict what will happen in the case that I don't have this clever sine-based square oscillator, but I actually have a geometrical waveform? So as you know now, aliasing will occur, and therefore what?
Still, they're gonna be harmonics mirrored.
They will be mirrored, exactly. So if the fundamental frequency is climbing up, what happens to the mirrored harmonics? It's going in against the mirror. It's reflected back. So the aliasing harmonics will do what? They will climb down, right? So it's a mirror, right? I'm pushing this spectrum into the mirror, and everything that folds back will start coming down. So listen out for this. Can you hear something climbing down? This is a monotonous rise for 500 to 5K. Okay, so it's huge amount of trash happening. So why does it happen that I have them going up and down? I don't have them coming down monotonously, but they seem to go wee, 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 wee. What's this? Well, it is the second mirror. So we actually have two mirrors. One is the Nyquist frequency and the other one is 0 hertz. Because if I throw a signal into negative hertz, it is actually the same signal as if it was positive. I mean, you could get into the details and you could say that it's a sine wave rotating in a different direction. Okay? So what is this sine wave rotating? How does sine wave relate to rotation? Because you see, it's a kind of funny thing. I don't know if I've said it last year. It keeps entertaining me 24 years later. Because back then I was in a class of electroacoustics back then in the Netherlands. And the teacher showed a sine wave, drew a sine wave on the board. And he said, well, this is a sine wave. And you might expect it sounds wee, 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 but no, it sounds wee. And he managed to repeat it 3-4 times within 90 minutes of the class. And it I don't know, it didn't really, I mean, it's still very traumatic for me to remember. With the distance at this stage, I'm kind of okay, that's funny, or it's sad, or both. But it definitely shouldn't be disturbing to the extent it was. Okay, so what is the constant thing about the sine wave? I mean, it goes up and down, right? But it doesn't go up and down, right? So there's something constant about the sine wave. What is constant about the sine wave? The frequency. And what is the frequency? What does the frequency depend on? Period duration. Period duration, but very close. Wavelength, I think I'll probably accept that one as well. Period duration. So this actually means that whatever I do in the single period of a signal, right? Whatever I do there, the only thing that I will get is harmonics of that fundamental frequency. Right? So I'll probably try to do that as well, although it's a bit more complex to show you. Let's stick with the simple things here. Okay, so this is my pulse wave. I have a sawtooth wave. I have a triangle wave, all nice and well. And we've discussed aliasing, right? So this is the basic thing that happens. Now, here we are looking at multiplication now. Okay, so I'm kind of repeating stuff from last year, but that's all right. So I will multiply, what did I say, 150 times a sine oscillator at 200 hertz. And actually you hear it as well. It's the bass, it's the 50 hertz, and what you hear above is the 350. And here you see it. This is the 50 hertz peak. This is the 350 peak. Okay, so why is it so ugly? Why don't I get a decent peak here, but I get these staircases? Any ideas? So this is the basic fallacy of spectral analysis. In particular, of fast Fourier transform, which is typically used for spectral analysis. And what you can conclude from this, and otherwise read all about, is that it has an issue with resolution for lower frequencies. So you can imagine that if I play a 50 hertz and a 30 hertz and a 70 hertz sine wave together, I'm not going to be able to distinguish them visually. Unless what? So this is, I think I didn't discuss much, but it's kind of common knowledge, typically, that if you increase the FFT size or the window of analysis, you increase the frequency resolution. But if you increase the window size, you lose a different type of resolution, namely, so I gain frequency resolution, but it's actually quite logical. If my analysis window is 1 second, then this means that I don't know what within 1 second when something happens. I just get a global picture of what happened within a whole second. So I lose time resolution, okay? So I don't know if any of you are, curious in some physics and stuff like this. We have a thing called Heisenberg's uncertainty principle. And it's a kind of a relative to this, because actually if you measure the velocity of an electron very precisely, if you have a high resolution in velocity measurement, you cannot measure the position very precisely, and vice versa. So if you get into the position, you cannot measure the velocity that well. Okay, cool. So you are seeing it happen. This is multiplication of two sine waves. So what happens if I multiply two sine waves of the same frequency? What will be the higher sideband? 400. And what will be the lower sideband? 0. Excellent. What is 0 hertz? Do you guys know?
7.
Yes, it's inaudible. How does it present itself in a digital, by the way, also analog system? It is what we call DC offset. Okay, so 0 hertz means that the period is what? Period duration is how much? One over 0? 0 over 1, sorry? 0 over 1? How much is 0 over 1 over 0? No, 1 over 0. Right, so hertz and period duration in seconds, second and hertz, relate to each other reciprocally. So hertz is 1 per second, and second is 1 per hertz. This is how you calculate back and forth between period duration and frequency. 1 divided by 0 is how much?
0, 2, 1. No, nothing.
No, they say it is undefined.
Yeah.
Right? You cannot divide by 0, so to speak. I kind of think, by the way, in math, there's about 5-6 types of infinity. And it's probably one of them, but I'm not even sure. In any case, it's undefined. And it kind of makes sense because a 0 hertz frequency does not have a period. But it has potential energy, which is your DC offset, which is actually the middle, the symmetry line, which is normally at 0. Right? So if you have a neatly balanced bipolar signal and you add all the samples together, they end up at 0 because the amount of positive and the amount of negative equals out. If you add them all up, you get a 0. So they're centered around 0. If there is no DC offset, DC stands for direct current, AC stands for alternating current, AC-DC. Yeah? So actually, you could also call it a DC component of the signal, which means that there is a fixed voltage in analog domain, or there is a fixed value in the signal like that. So if I do this, that's what you get. You get a 0 hertz energy just there at the bottom. You get a 400 hertz, and you see it here, you actually get a unipolar signal. Why? Where did the negative values go? I mean, if I add them together, what will happen if I add them together instead of multiply them together? Well, it's not a 400 hertz anymore. It's back to 200, and it's clipping like crazy. Why is it clipping?
Because when we add sines with the same frequency, just add more amplitude.
Yeah, it also has to do with phase, by the way, right? So if I add two sine waves of the same frequency, of the same phase, okay, then what happens is that the original sine wave, let's call it the first sine wave, it has a range. What is the range of values coming out of this oscillator? What is the minimum maximum value of an oscillator output?
0400.
No. Those were the frequencies. Okay, so don't mix range with frequencies. So output range, or if I want to, be very specific, it is the range of amplitude values at the output of the oscillator is typically full range. What is the full range of a digital audio signal?
-1 to 1.
Exactly. Yeah. So that's my range. So what happens if the two sine oscillators are in phase, then the +1 peaks align, and +1 plus +1 is 2. And the minus peaks align as well. So -1 plus -1, right? You're adding the signals, you get -2. Okay? So that's why it's clipping. It's actually out of range. Okay, so who can reason now what happens if I multiply these two sine waves? So again, the peaks align, the troughs align. Okay? So when both are peaking at 1, 1 times 1 is how much?
1.
Yes. When the negative peaks align, -1 times -1 is?
+1.
+1. That's why. You see, because every negative value squared is the positive value, right? So as soon as this oscillator, both of them in sync, drop to negative values, they will actually make the values positive. And actually you see it here now that the center of the signal is 0.5. So this is the DC offset. This is my DC offset at the stage. So actually I do get both sidebands. I mean, it's a clean sine wave, by the way, but I did get the lower sideband as well. Cool? All right. Now, what would happen if I change, let's go back to 150 and 20. So we had this one. Okay, so I got two sidebands, one at 50, one at 350. But now I will make this one unipolar, 0 to 1. What will happen? I said it just now, about 20 minutes ago.
Can you please repeat the question?
What will happen if I make the modulator unipolar? So you see, initially both of these were bipolar signals, -1 to +1. And now I've taken this second one and I've made it 0 to 1. I've made it unipolar. Hmm?
It would be unipolar.
We've just discussed this. The first option is called ring modulation, and this second one is called amplitude modulation. And the difference spectrally is that in this case, the original frequency does not disappear. Right? So I have the 150 here. If I didn't have the, remember this graph, right? If I go back to the previous state, oops, there is no 150 hertz. If I make it unipolar, there is. So you can say that if I modulate an audio signal with a sine wave, which is bipolar, then I will lose the original signal. I will get only the sidebands. But if I multiply it with a unipolar sine wave, I retain the original signal and get the sidebands, like here. Right, so I end up having, oh, that's a comma. What? What's up here? Did I leave out? Oh, that's a comma. Okay, so I retain the original 150 hertz. How can I retain the 200 hertz?
What was original here?
Well, here, what I've done, I have two oscillators, 150 and 200, right? If I multiply them both bipolar, I get only sidebands. The originals disappear. Now, what I've done here is that I've made the 200 unipolar, and therefore, I retained the other one. So logically, if I want to retain the 200 instead of 150, I make the other one unipolar. I think we might have to change the teaching plan completely, because this would be, the basics. This is like talking English, in sound synthesis. If this doesn't click and you cannot think around this way, we might end up playing in Max MSP and making funny noises instead, because this is, this would be the basics, actually. So if I don't make this one unipolar, but I make the first one unipolar, there it is, the 200 hertz stays, and I get the sidebands around it. So what are the sidebands around it then? What are the other two frequencies? Are you guys scared of me, or what's going on? We've just asked this question 2 times in the past 20 minutes. Sum and difference frequencies are 1 plus the other, 1 minus the other. Therefore, 350 and, yeah. Is there something I can do? Okay, well, let's chug on. I'll do just a bit more just to cover some ground. We'll have a break, and then we'll see if you guys can code basic stuff. I mean, you've had 2 semesters of SuperCollider. So if you prove to me that you cannot code basic stuff, then probably gonna talk to Balázs and quit SuperCollider. It doesn't make sense to push something that doesn't want to go. So, logic. What would happen if I multiply band limited square wave with a sine wave of, I'll do something funny, 44 hertz? How can I reason about this? Well, actually, I've just told you that this square wave, a digital square wave, doesn't look like a square. Instead, it is made of?
False.
No.
Oh.
It is made up of
Sine?
sine waves, right? The simplest, or actually spectrally most narrow signals we have, because we know what are the constituents. We can synthesize those sine waves until the Nyquist frequency, and they add up to be a decent square wave. So if you think about this, can you come to a conclusion what will happen? because I can say at this stage that I'm multiplying a square wave with a sine wave, but I can also say that I'm multiplying a sum of sine waves with another sine wave, right? Because this square wave, depending on the frequency, will have 2, 3, 4, 10, maybe even 15 sine waves, probably not more. So what will happen? Well, this is basic math, right? So if you have a plus b plus c times 3, this is equals to 3a plus 3b plus 3c. This is the same situation here. So what I will have then, can anyone reason? What are the sine waves that make up a 500 hertz square wave? The lowest one is? Why 50? Well, 500. Right? So I have a square wave. Shall we look at the square wave again? So my square wave at 500 hertz has these harmonics. Each harmonic is a sine wave, right? So the lowest one is 500. The next one is 1500. Excellent. Cool. So this means, let's do a simpler one. Let me take the 5K, right? So if I have 5K, I actually have only two harmonics. Or I could say I have only the second harmonic. Because I have the fundamental, so I have one sine wave at 5K and another sine wave at 15K. So if I multiply this with 44 hertz sine wave, what do I get? So I have A plus B, this is A plus B, 5K plus 15K, times 3, or times 44, right? So I get 44A plus 44B. So what happens if I multiply a 5K sine wave with a 44 hertz sine wave? I get sidebands, again. What will be the frequencies of these sidebands? Sum and difference, therefore, what is the sum? Sum is 5044. And the difference is 4,966. Okay? So actually, visually, and will I retain the 5K sine wave? Or will it disappear?
Yeah,
Disappear, because it's a bipolar modulator. Okay? So actually what I expect is, essentially, instead of this one center frequency, I get two sidebands, the center disappears. What happens to the 15K sine wave? The same thing, gets sidebands. The higher sideband will have frequency of 15,044 hertz. The difference will be 66. Okay? So that's what happens, right? So actually, what I'm saying here is that I'm multiplying a square wave with a sine wave. And in order to understand what will happen, I figure out what are the sine waves inside the original square wave. And then do the math, so to speak, to each one of those components. And then I know what's going to happen. Let's verify this. So I have a pulse at 5K. Well, the thing is that the resolution is not high enough. This is now two pulses, two spectral peaks. But I don't quite see them. How can I make it visible? How can I pull the peaks apart? how can I make the sidebands more distant to each other? No. So what does it depend on? What is the distance of the sidebands here? Between the two sidebands. So we had a 5K signal. Top sideband was 5044. Bottom one was 4966. What is the distance between the two sidebands? 88 hertz. Which is why? Why is it 88 hertz?
Multiplier is 44 if we increase the...
It's not the multiplier, it's the frequency of the sine wave, the frequency of the modulator. Okay?
Yes.
So the distance of the sidebands depends on the frequency of the modulator. If I want to increase the distance of the sidebands, what do?
Increase the value of the sine.
Not the value, the what?
Frequency.
The frequency of the modulator. Let's try it. So if I go 144, you see? They're increasing. So what I can also do, now that I know how to use a ramp, I can put a line here, start at 10 and go up to 500 in 10 seconds. And you see how they're spreading apart? One is climbing up, the other one is climbing down. And there it is. At this stage, the modulator frequency is 500 hertz, so the distance between the sidebands is 1 kilohertz. Excellent. Cool. So, what will then happen if I run the same thing with a 500 hertz band limited square wave? Well, the same thing, the departure, the distancing of the sidebands will happen for each of the harmonics, right? Namely, like this. Yay. Okay, shall we make it a bit more fun than this? Let's see what happens if I make them go back and forth sinusoidally. Sine oscillator, okay? I'm gonna use, let's use 30 hertz so it doesn't really become an audible frequency. And then I need it to be in the range of, well, 0 to 200. Can anyone explain what is happening now? So what's happening is that I have the basic square wave with the harmonics, and I am producing sidebands because I'm doing a bipolar multiplication. But the sidebands distance is shrinking and increasing rapidly, 30 times per second. Every harmonic is doing something like this. Distance close, distance close, distance close. And because 30 hertz is at the frequency where I cannot distinguish separate events, what I hear is essentially a single buzz, right? It becomes a sensation of a continuous timbre. So if I slow it down, then I might be able to catch it. That's what's going on. The sidebands are moving back and forth. Okay, cool. So let's take a decent break. I think we'll have only one. We will finish by 8. So what I will ask you to do in the break is draw this. Okay, we've started drawing last week. So try to draw this scheme with 3 oscillators, the connections and the parameter values. And also, please set up a SuperCollider. Okay, so if you need to grab the machine from the corridor, do that. We could also move to the other, but there's also no machines in the other room. No, it's only empty desks, right? So you definitely have to move the machines, okay? I hope there is keyboards and everything. So I will call it a 20 minutes, a decent 20 minutes, so we will start at 7. This is still UK time. Okay, so 23 minutes. Please draw this and get the SuperCollider running. Here we go. So, Graphel. So what did we have there was something like a few oscillators. So essentially we had a sine oscillator and we had another sine oscillator which modulated the frequency. Okay, so the way I typically display this, there's different options, different ways. I'm happy to see other ideas as well. Is I typically say that this controls the frequency. Okay, this is something I've gone through last time. It's a bit of a repetition. So this means that the sine oscillator controls the frequency of another sine oscillator. Okay, now what's missing? I mean, if I give you this, can you code this? No, you're missing what?
Range.
Ranges, parameters. So what is it that we are missing?
The period of this modulation.
Yeah, essentially the frequency, right? So the modulation frequency, so there's multiple ways of doing this. I'm also happy if you just do something like this. And then it says it's a 5 Hertz modulator. But if you want to actually be more consistent with this thing, you could also set up another input and say that this is now just a fixed number 5. Okay, so you can do this as well. It really depends on what you like. Okay? Okay, so this is the modulator frequency. And what's missing as well? You just said it? Range. Okay. So what is the range in my code? Let's see my code. 0 to 200. Okay. So again, you can do this in multiple different ways. What I prefer actually is to declog it, meaning have less objects and have them be more informative. So actually what I would prefer doing here myself is saying that this oscillator has its frequency there and it has its range kind of next to it. Or actually, well, in this case it's fine because it's a sine oscillator, it's symmetrical. So maybe here, something like this. Typically I do this in a box or something like this. Okay, so this would be my way of saying I have a sine oscillator at 5 Hertz and the range is 0 to 200. But actually, if you remember from last week, we already had a situation where we had one oscillator and we needed to use it with 2 different ranges. So actually I did a split and then had a range box. You can also just put in range and in the brackets, whatever you do. So that's quite flexible. Okay, and then in terms of the code here, what are we missing? The pulse. Okay, so I have a pulse, which is pulse.ar at 500. And what happens to this pulse?
Goes to another block which says it's multiplying.
Exactly, yeah. So I typically create another bit of text here, which is an X for multiplication. Let's have a stroke. Let's have a shape. Oh, I'll have a circle for the arithmetic typically. Oops, oh, here we go. There is an X. Okay, so this is my multiplier box. And the nice thing about this is that, you know, you can kind of translate it fairly easily. Oh, God. I'm now in this mode. You can translate it fairly easily to max MSP. And you can also translate it to analog circuitry. This actually looks most like analog circuitry, to be honest. So this would be my multiplication of a square wave with a modulated sine wave. Okay, and then, well, some years back I used to have a little heart to balance my horrible temper and arrogance. And this year I'm gonna have this. I don't care. This is what I hear. Okay, this is my output. Make sense? Cool. So that's what I want to practice now in the second half of the class, that you actually get to understand it better and get some practice, because I mean, I do understand, you know, when I was in school 30 years ago, they were actually pushing abstract understanding. And, you know, you had to do things essentially blindfolded. And these days, you know, with all the computers and everything, it's very difficult, I understand, to deal with things which are not practical, which are not in front of you. So we shall attempt to do much more of that. Okay, so I will make a patch now, visually, and then I will ask you to code it. Okay? So let's do something funny. Yay! Let's take white noise. I like white noise. And let's ramp it. Okay, so you've seen a ramp already. I will give you all the clues needed. This is a line.kr. First argument is the starting point, let it be 1. Second is the end point, let it be 0. And the third one is duration. It will be 2 seconds. Okay, so if I now, I like this drawing. If I now propose to multiply these two signals, what do you expect to happen? Yeah, 2 seconds of white noise, and added to that, what is the one more thing it does? Well, it's a ramp. Yeah, so it drops the amplitude gradually. Okay? Go for it. Okay, I'm not gonna make it very complex to start with, but we're gonna build on it, so to speak. So please try and make this happen. Everyone's got it working. So we shall do SuperCollider, yeah? Forever. For the whole class. I mean, you know, it's a bumpy start, but hell, you know, every relationship, at least most of them, start bumpy. But I see you got the basic stuff going, right? So we can build on this, yeah? You feel like it? Let's do it. Cool. So what are we looking at here? So let's see, again, tricky question. A little bit of affirmation, but gets tricky very quickly. Curvature. That's what we've discussed, yeah? So how do I make this a sharper attack? So while you're thinking about it, I'll just quickly code it myself. So I have whitenoise.ar, and I multiply it with the ramp, which is a line.kr, starting at 1, ending at 0, duration 2 seconds, .play. Okay, so I don't want to change the duration. I don't want to change the starting point. I don't want to change the ending point. I want curvature. I want it to be and go down quickly like that. How did we do this? Yeah, so you remember that range 0 to 1 in terms of creating a curvature is the easiest thing to deal with. Because if I raise to an exponent or take the root, which is an exponent less than 1, then range 0 to 1 will always stay 0 to 1, because 0 to the second power, to the 100th power, to the 1 over 5 power, 0 to any power is 0, and 1 to any power is 1. So the only thing that will change is the curvature between 0 and 1. Okay? So, if I square 0.5, what do I get? Which is 0.5 times 0.5? 0.25, right? So this means that if I square my ramp, I have a ramp going from 1 to 0. If I square it, which way will it curve? Up or down? Down. That's it. That's the answer to the riddle, right? So the only thing I need to do is square this. Now, because SuperCollider goes in order rather than based on math priority, I'm going to put this in more brackets. And I'm going to square it. And if I take it to the power of 7, you see, I'm slowly getting a much more percussive sound because the attack is increasingly shorter. I mean, the attack is always 0 because it just starts at 1 and drops. But the rate of dropping is increasing such that I have a shorter sound that I perceive. 30? Okay. Now, the next task is to, well, first of all, draw this, but that's not a huge task, so I'm just going to quickly do it. So what I've done here is I've taken the power. Well, this is kind of the usual math thing for power. But I could do 2 stars, I could do anything, as long as people reading it know what I'm doing. So what I've done here is before the multiplication, I have raised it to the power of, I don't know, whatever at this stage. Now it goes automatically on this one, is it? Stroke, no stroke, fill, no fill. Let me just copy one of these. Okay, so I've taken it to the power, I don't care, 15. And I got a much more appealing sound. Make sense? This is what I've done. Okay, so what I want to do now, and I'm gonna explain it in words, and you can either try to draw it first or to code it first. Let's see how you get on. So what I want to do is I want to low pass filter the noise. And then I want this filter to also drop. Right? So now what I'm doing is I'm dropping the amplitude using a ramp. And I actually have a curvature control. But just to start with, let's have a filter that will also drop the frequency. A low pass filter filtering the white noise that drops the frequency such that the attack has more high frequencies and the decay is more low frequency. Get it? Okay, let's see it. So you can try by drawing or by coding first, or both, or whichever way you like. Okay, so we're getting there. So essentially what we're doing here is we're filtering the white noise. I mean, I could filter the actual amplitude enveloped, ramped sine wave, noise as well. But actually, essentially what happens here is that I have a low pass filter, and into this low pass filter I put my noise. Is this plenty and sufficient? What am I missing here? Frequency, very good. So now you've seen that if I want to do this trick, actually here the first argument is the input, which I already have there. And I really don't want to put 2 Eugens in a single box. So actually in this case, what I prefer to do, And as I said, you can always come up with things you might prefer better, is to actually specify this is the input and then get another arrow in there, which will be the frequency. And then I can, then I can actually make sure that it's clear that the input is the white noise and the frequency as well. I didn't specify it. Let's do 4K. Looking good? Excellent. So now let's see how this works out in code. So actually, I am putting white noise, I'm embedding it into this filter. Okay? So I'm just working a filter around it, and I'm adding the second argument, which is my 4000 hertz thingy. Okay, now at this stage already, I will suggest that we start using variables. Okay, so I'm going to show you how I will separate this into variables for clarity. So, and actually I will be very painfully detailed at this stage. I will actually say the source is whitenoise.ar. Okay. Filtered signal is LPF AR with the source in there and the 500. Well, I'm not going to put that in a separate variable, at least. And then I will have my ramp, which is the line. And I will include the curvature. And then my final signal, my final output will be filtered times ramp. Looking good? Well, I did 4000 a second ago. Okay, so obviously it's up to you. And, you know, when I was studying this, I always had this sense of, okay, I want least possible characters. And, you know, if I read my code from 20 years ago, I don't read it, you know, because it's just convoluted. It's not made to be read. And luckily, no one wants to read it either, so it's not a huge problem. But choose your way. You know, I'm also going to pay attention to how you guys develop, think, what is your preference here, and then we'll take it from there. Okay, so this was the first step. We have filtered the noise signal. Now, we want to ramp the filter frequency. We want the filter frequency to drop from 10,000 to 100 hertz. Okay? So, go for it. Again, you can start with the drawing, or you can start with the code, or you can do a bit of both. So we want to extend this such that the filter frequency is not fixed at 4000 hertz, like it is now, but it also uses a ramp that lasts 2 seconds and drops from whatever I said or whatever you come up with. Makes sense? Okay, try it. It's late, huh? I can't quite hear, but I imagine. So the point is that this is the frequency, cutoff frequency of the filter. And instead of a fixed value there, yeah, source, drop, filtered, no, it's still fixed 4000. You've just multiplied something else into it. So this is the number 4000, which is currently the fixed frequency. Here it is in the diagram, and here it is in the code. So actually that is the one that you want to replace with the line.kr. Okay, so that's the easiest thing. I mean, here I can do this fairly quickly by saying this becomes a line kr instead of a fixed value. Okay, and then obviously I just need to change the values. I drop it from 4000 until 100 in 2 seconds. Okay, so that's the diagram, and then in the code I say in the code I can just do it in here. In fact, I'll just recycle this line. Here we go, change the parameters 4000 to whatever. Okay, now I don't quite hear it drop because my curvature here is fairly... Okay, now actually I said, well, we could do the curvature for the frequency drop. How would we do it? Do you remember what was the easy way of getting this curvature thing done? So the easy thing to do was to work in the range 0 to 1. Because then you know, if you start 0 to 1 range, you can apply curvature with exponentiation either way, and then you can scale it up or down or wherever you need it, as you wish. Now, there is an x line, by the way, which will generate an exponential line, which will be slightly more suitable for the frequency. And you see it's actually more audibly dropping. This actually sounds more like a linear drop. If I don't have the exponential line, I have the linear line. You see, it stays up in higher frequencies much longer, which makes sense. Okay, great stuff. Now, how do we make this more exciting? Distorted. Okay. Or modulated. Or both. Well, the thing is, I'll probably leave this for you guys to experiment by tomorrow. But just to make sure, do you understand what does distortion do spectrally to a signal? Add harmonics. So if I distort noise, what do you expect? Noise. Well, actually, it's a good thing to try out. I mean, my guess is that if I radically, hugely, horribly, tremendously, aggressively distort noise, that I might be able to hear it. But if I don't, I might not. Okay? So what kind of distortions are you aware of? How can I distort a signal? So, let's start with the sine wave just to make sure we are getting the right thing going. So I have a 400 Hertz sine wave. How do I distort it? Well, did I not? I think I did a bit of distortion last year, no? Maybe not. My memory doesn't serve me. Anyway, we'll go into it at some point. But probably the most straightforward is the 10H. Okay, so this is your cotangent. So if I watch this on frequency scope, and if I have it, that's what happens. You see, so it's kind of rounding it off, and spectrally I have harmonics happening. How do I increase the amount of distortion? Or decrease the amount of distortion, for that matter? Where? Cotangent, hyperbolic tangent, as we call it, has no parameters. It's just a transfer. It's a one input, one output type trigonometric operation.
Multiplication.
Where and what? So that's the thing to really remember well, is that the amount of distortion, and if you play guitars or have pedals or other things, you know typically it's called drive. And what it is, drive is gain before nonlinearity. Okay, so I just said a minute ago, you remember that if there is a nonlinear process in the chain, then the order of elements matter. Distortion is nonlinear, filter is not. So in this case, if I have a distortion in there, the order is relevant. If I have a gain stage, a multiplier, before the distortion, then I will increase the strength of the harmonics. But if I have the multiplier after the distortion, I won't. You see, because the distortion is the nonlinearity, gain is a linear process. So if I have it before, it's a different than having it after. And typically, with distortions, we have the drive parameter, which is nothing more than gain before the nonlinearity. Okay, so what I can do here then is I can use the multiplier parameter, and I can say 10. And immediately, you see much more harmonics, much louder. What I can also do now is I can drop it, and I can say, how about I drop from 10 to 0 in 2 seconds. And there you see it happen. Yeah, I can also, well, actually the X line is problematic with 0. You cannot use 0. So I'll have to fudge that. You see? It's starting to give you the little electronic-y thingy. The kind of 50s sounds. Okay? So, let's do it. Let's see what happens if I heavily distort noise. Okay, so I'm taking white. What happens? I'm taking white noise. Okay, and I'll do it the nice way. So my source is white noise. Okay, then my drive will be source times 10, and then my output is drive.10h. Okay, so this is my drive of 10, this is my drive of 0, this is my drive of 100. Doesn't really do much, yeah? Well, we can obviously, now that we know how, we can try it, and let's say, let's go with the line.kr. Let's start at 0. Why not? And let's go to large number, and let's take 100 seconds. Nothing. How unfortunate is that? However, the nice thing is that I can probably get some more interesting noise if I multiply it with some oscillator. So if I take a sine wave oscillator at 300 Hertz, you see it gets some kind of texture to it. And what I can also do is I can take a sawtooth oscillator at 300 Hertz. You see? So this is actually your noise modulation. Can you reason what happens when I multiply white noise with a sawtooth oscillator? Sidebands. You don't even have to think. Multiply signals, sidebands. What you have to think is what kind of which sidebands, what's happening. So in this case, what's happening is that white noise is a flattish spectrum. So you actually have, all the components. And then I'm multiplying it with a sawtooth wave, which I can think of as multiple sine waves. So I'm actually taking the noise spectrum, let's depict it like this, I'm pulling it apart, sidebands, by 300 hertz. Second harmonic, sawtooth wave has all harmonics, right? So second harmonic, even further pull, even further pull, and even further pull. So actually I'm multiplying this noise signal many, many times. And, well, actually here I'm also distorting it. Let's see if that makes a difference. So this is with distortion, without, not much, oops. So, let's just see the spectrum and call it a day. Frec scope. You see, it's curious because what I'm doing is I'm taking a flat spectrum, pulling it apart many times, duplicating it like that. It's still a flat spectrum, but it's obvious that there is a difference. There is an audible difference, which is really curious. So let's see how this develops throughout the spectrum. So I'm going to run this from 0.1, and I'm going to do it exponentially as well, to 10,000, and I'm going to run it in 10 seconds. Oops. Did I mess something up? 10 seconds, missing a bracket, yeah? That's done. Okay, guys. Good work. I think we have something which we can build on, yeah? I'm going to avoid too much theory, but, it's a game we play together. So, the more you tell me, the better I can relate to what is your interest, motivation, and so on. But I guess we just want to make cool sounds anyway, right? Which is the point of the practical sound synthesis in this semester. So we're not going to do Max MSP, we're going to do the SuperCollider, yeah? Do the real thing. Good. Thanks for coming, and I will see you tomorrow.